At the quantum level, time appears perfectly reversible. The fundamental laws governing quantum mechanics, whether described by Schrödinger's equation or quantum field dynamics, allow for a system's evolution to be precisely retraced if all momenta are reversed. This microscopic reversibility implies that no preferred direction of time exists in the fundamental equations, aligning with the idea that quantum fluctuations and particle interactions operate symmetrically when isolated from external influences. However, at the macroscopic scale, irreversibility dominates. The second law of thermodynamics dictates that entropy must increase over time in an isolated system, providing a statistical arrow of time that governs large-scale phenomena. Whether it is the dissipation of heat, the breakdown of ordered structures, or the one-way progression of biological and cosmic events, macroscopic reality exhibits an undeniable temporal asymmetry. The challenge lies in explaining how the pristine, time-symmetric nature of quantum mechanics transitions into the irreversible, entropy-driven world of everyday experience. This transition is mediated by mesoscopic fluctuations, the intermediate scale where quantum coherence begins to unravel, yet statistical laws have not fully asserted dominance. In this regime, systems experience partial decoherence, where quantum superpositions degrade due to entanglement with their environment, but without complete loss of memory of past states. These mesoscopic interactions introduce probabilistic deviations that, when aggregated, drive systems towards statistical irreversibility. A prime example of this mesoscopic mediation is superconductivity in magic-angle trilayer graphene, where quantum coherence persists over macroscopic distances, yet remains susceptible to fluctuations that can disrupt the phenomenon. Similarly, composite Higgs models illustrate how emergent interactions from fundamental quantum symmetries lead to large-scale, effective field behaviors that break time symmetry at higher energy scales. Astrophysical observations further reinforce this interplay. Weak lensing shear in cosmology captures how microscopic quantum variations in early universe energy densities influence large-scale structure formation, subtly shaping the universe's irreversible evolution. Likewise, gamma-ray burst spectral variability reflects how microscopic quantum fluctuations in high-energy astrophysical events lead to macroscopic directional outcomes, such as energy dissipation and irreversible expansion. Ultimately, mesoscopic fluctuations act as the bridge between two seemingly contradictory realities, the microscopic world of reversible equations and the macroscopic domain of entropy-driven evolution. This interplay suggests that irreversibility is not an inherent contradiction to time-symmetric laws, but rather an emergent property arising from the cumulative effects of decoherence, statistical mechanics, and many-body interactions. Time's arrow, then, is not imposed by fundamental physics, but is instead a natural consequence of scale-dependent interactions, revealing itself only when the sheer complexity of a system demands it.